So first we talked about like computational feasibility. And this leads us to something that I call the Frugal universal prior. So what is the Frugal universal prior? It's not something that actually exists. It's a mythological creature. It's something that I believe should exist. Like, we talked before about bridging this gap between bounded Solomon prior, which is infeasible, and here there's like classical learning theory stuff, which has things like small MDPs, support vector machines, and those are things that are kind of feasible, but impoverished. They kind of describe hypothesis classes that are, in some sense, too small to capture, interesting structure. And the Frugal in like on this scale here, somewhere allegedly hides the Frugal universal prior. I mean, it's not really a linear scale, but like conceptually, like something that would be, on the one hand, would it allow feasible learning algorithms, on the other hand, would allow a rich class of hypotheses. And okay, question is, how do we get such a beast? Where do we get it from? Okay. So there's like different like directions, different approaches we could take to kind of find these two. Like one approach could go from like approach 1.1 could be like trying to create a theory of deep learning. Because like we know already that deep learning is like de facto doing something like this. Like it's like learning some very sophisticated, complicated hypothesis somehow. So it must be doing something, might be learning something which is close to the universal prior, arguably. So we understood how it actually works in terms of like what generalization properties it satisfies. That leads us to the answer. But and like there are different like approaches to this thing, like singular learning theory. But I'm not personally not like focused in this thing because a lot of people are trying to get it from this direction, and yeah, it's good, but it's not what I want to do. I mean, there's another argument for why not to do it, which is like this thing could immediately lead to some advances in capability. Of course, a different way to arrive the theory of Frugal universal prior might also lead to advanced capability, or not. It's not, but in any case, even if we assume this is a good idea to do it, then a lot of people are really trying to do it. So I'm not concerned myself with this thing too much, but I guess this is more like a strategical choice, like conceptually that's a kind of the only research approach. What I'm more interested in is thinking about compositional learning theory. So compositional learning theory, what is it? It's also some kind of mythological creature that doesn't exist yet. So we're talking here about like this Frugal universal prior is supposed to be something that's kind of described as very rich class of hypotheses, right? But I mean, how rich? Right? Like no free lunch means that you can describe everything. There must be like some implicit assumptions in your prior in order for you to be able to learn it, even the statistic. So in the Solomon prior, the kind of assumption is that the universe can be described by a short program, something like that. So what other assumptions can we sort of make that would be still very, very general, very non-constrained, and yet we could explain it? So if you kind of look both at the universe and at how we approach problem solving as humans, then kind of some things stand out as possible properties that can be exploited or like assumptions that can be exploited in learning algorithms. There's not like that many of them actually, but so what kind of properties would that be? There's like things like locality, right? That kind of the universe can be like described locally, and like things too far from each other don't interact with each other too strongly. Right? There's things like there's like causality, which is like a closely related thing, but maybe it's kind of slightly different thing. Right? We can kind of describe the universe as some kind of a causal network. And this maybe also imposes some structure that's not obvious. There's like things like time scale decomposition and like spatial scale decomposition. So like time scale decomposition means that we can kind of describe processes that happen in a certain time scale while it's sort of mostly ignoring things that happen in other time scales. Like, we can kind of build some models of geology that don't need to have that don't really pay attention to like what happens on the time scale of like minutes, hours, or even days, right? Which can ignore just all the processes that are just so too fast. So you just assume that you're right with the framework. There's like spatial scale decomposition, which is something that's kind of happens all the time in physics. Whether there's in Earth words like renormalization groups kind of related to that. Where like physicists like to talk about how like you have some effective descriptions of physical systems on a particular scale, you don't care about the microscopic details. And like, if we didn't have this, in some sense, we would not be able to discover physics at all, right? Because like the reason we were able to kind of start with like Newtonian physics and then go down to like, thinking about materials and then about like molecules and then I go like subatomic particles and like stronger and stronger forces or like higher energies and smaller spatial scales is that kind of the physics on the big space scales can be described in some simple way while kind of ignoring all the microscopic detail. So this is kind of examples from physics, but you can also think about just more kind of real life examples like divide and conquer, right? So, but this is kind of related to all of those previously. But like often when we want to solve some complicated problem, we divide it to different parts that can be solved independently and solve each of them. Right? But this is something about the domain, some property of the domain that such a decomposition is even possible. If you look at all of those things, then for me, all of those things sound like they want to be talking about compositionality. Because all of those things are talking in different ways about the fact that kind of the universe can be described with models that are made of parts that can be kind of analyzed separately. Right? We can talk separately about different time scales, different spatial scales, or like different nodes in the causal graph or different spatial locations. So there's some way to the universe is not just one kind of one monolithical blob, but I mean it's more like a thing about and we shouldn't be it's like actually a philosophical question here. We're talking about the map or the territory, but it's in some sense it's like it's a combination of both. So in the universe, we can model it pretty well by models that have like kind of independent parts inside them can be analyzed separately. So it feels like some sort of compositional structure is the key to what kind of mathematical beast is this frugal universal prior is going to be. So this kind of naturally leads to the quest of let's look for hypothesis classes that have some interesting mathematically natural compositional structure, and look what kinds of compositional structure would allow us to create efficient learning algorithms for those hypothesis classes. And this is actually, I think, a supernatural question from a purely mathematical point of view, which is makes it maybe kind of a little surprising how relatively little attention it received, because kind of historically learning theory focused a lot about thinking more in terms of those kind of continuous, kind of analytical, in the sense of like analysis, calculus kind of things, like support vector machines and kernel methods. We're kind of thinking about like some functions, families parameterized by something, polynomials or Gaussians or whatever. And kind of much less attention was paid to thinking about compositional structure, which has like this more sort of combinatorial nature, like things composed from. Well, there's a theory of Boolean circuits, learning Boolean circuits, which might be a little bit. So compositional learning theory is this kind of general idea, and it also feels like it wants to be connected to categorical systems theory. Because like categorical systems theory is this kind of domain that some category theorists come up with, exactly when we're like studying, trying to come up with lots of useful mathematical language to talk about compositional structures. And it seems like some interesting, like there might be some interesting connections to be made there. It is actually an interesting fact that the Polytope MDP, the whole Polytope MDP framework turns out to be a very good fit for one of the models of categorical systems theory that David just admires too often. So it does feel like there's some hints that there could be some useful, fruitful connections there. Okay, but what are kind of more concretely, what kind of examples, how do we approach this? So
I didn't get why Boolean circuits might help, like, isn't it?
So what might help?
Why might Boolean circuit theory help?
Yeah, Boolean circuit theory. Yeah, Boolean circuit theory is interesting because it is kind of an example of something which is more like a combinatorial type of structure. Mostly it just failed to produce some very interesting positive results. Like the Boolean circuit theory, what we know there is that AC circuits are like circuits that are made from AND and OR gates, which have a lot of inputs, like unlimited fan out. So if they're shallow, so it means if the depth of the circuit is of 1, then you can learn them in quasi-polynomial time, which is it's not polynomial time, but it's not exponential, so it's something anyway. You can also, if you also add gates that do some kind of arithmetic model of E, it's like gates. I think that what happens in the you can add a gate which kind of counts. If I remember correctly, it just counts whether the number of on inputs it receives is divisible by p. Then this thing also has a quasi-polynomial time algorithm. But for example, on the negative side, if you add a gate which does a majority vote, right? So it's like a gate where there's a lot of inputs and like outputs 1 or 0, depending whether there's more zeros or more ones in the inputs, then those things are already cryptographically hard to learn. So circuit learning theory, there's like some interesting results there, but it's not like it's kind of there's some like powerful no-go theorems there, and it feels like if you want to go around these theorems, then you need to be looking for some kind of a different structure, and this probably requires a different approach.
I mean, I only barely saw this mentioned a long time ago, but what about those like chasm at depth 4 kind of results? I don't know if you've seen those.
Chasm at depth 4,
so don't they kind of say that constant depth doesn't give you much? Or I don't know.
That's a slightly different thing. We talk about like expressiveness of circuits as a function of depth, and I myself only vaguely remember. There's some open problems there which are not solved and considered very difficult, but. I mean, the problem here is not even with the depth, right? It's like even for shallow circuits, if you allow majority of gates, then it's already intractable. So it just feels like, the examples of circuit families for which we have efficient algorithms still don't seem to be like sufficiently rich hypothesis classes to to do the thing we want to do here. Another thing is that, in some sense, there's like another issue here, which is we want to have some kind of an open product, right? So we want to like obviously description complexity needs to be like part of the story here, and this might actually fit very well with compositional descriptions. Because like if you have some kind of compositional description of your hypothesis, then you can say, okay, the size of the description, how many like atomic components it's built from, is like the description complexity. But for circuits, that means like that you're just looking at the size of the circuit, which is the size of the circuit is actually related to time complexity. So it doesn't feel quite right, because it seems like you want to have things which are not just time complexity related, because like description complexity and time complexity are really different things. And there's also the question of how do you deal with sequences, right? Because circuits, they have like a fixed number of inputs. So if you want to be thinking about like sequences, then you want to do some kind of recurrent circuits or something like that. And I'm not actually sure where learning recurrent circuits is something that has been studied much at all. I mean, intuitively, I feel like this is not the right structure. That doesn't seem like if that was the right structure, people would already have so much better understanding of this question, I think.
Yeah, I was just like, how was it related? how does it help with the compositionality? Because you mentioned it as something that you considered but then dismissed to help with
I mean, you can say circuits are kind of related to compositionality because like circuits are also like composed from parts, right? But the fact that circuit learning is so hard means that this is like not a sort of compositional structure that is especially easy to exploit by learning algorithms.
I mean, I don't know, like, you can also like compose Turing machines in some way. I don't know, I just don't see like the difference and they kind of equivalent.
I mean, yeah, if you come up with any number of compositional structures, the interesting question is like what kind of structure actually like leads to efficient learning algorithms, right? What kind of structure can be exploited by learning algorithms?
Are you looking fundamentally for like a compositional structure where like the description length in the compositional language like is like a suitable proxy for like some hypothetical ideal description length, like fixing some programmable language?
Yeah, definitely. So, what kind of compositional structures I think is interesting to look at? So this is currently like all pretty open and speculative, but there are like some examples which, or like some directions that I think might be interesting to look at, and direction. So one direction is like string machines. And I mean, string machines are mostly interesting because it seems like kind of finite state machines are a pretty natural starting point. Because, like, for example, in reinforcement learning theory, we have like MDPs. But on the other hand, we don't want to scale the number of states. And then we're like asking ourselves, okay, what kind of compositional structure can we come up that allows us to build finite state machines? And it seems like thinking about like transducers which convert, kind of diagrams for transducer state data and feed it into other transducers is like one very kind of natural way to do it. So in string machines are kind of talking about that. So there's actually a very related thing, closely related thing called algebraic automata theory, which I think is, so algebraic automata theory is something that started with the work of Frugal and Rhodes, who showed that there is a certain way to decompose finite state machines into prime components, which is analogous mathematically to the decomposition of finite groups into simple groups. And the analogy is actually pretty close in the sense that kind of the prime building blocks into which they decompose it are actually correspond to simple groups and also to another special type of component that doesn't occur in simple groups. But it's just pretty fascinating as a purely mathematical thing that kind of the classification of simple groups is like this enormous mathematical project that took decades to complete and like people are still working on properly organizing all the proofs and checking them. And this is kind of interesting that it can come up in the context of finite state machines. And it is actually pretty similar. Like the type of compositions they do there is exactly like behaves like transducers feeding data into other transducers, but in a more constrained way. So string machines are string machines in general are obviously too strong in the sense that it's very easy to build something with very high computational complexity. So you obviously need to add some constraints to get something feasible out of it. And maybe if we add the right constraints, we'll end up with something that looks more like algebraic automaton theory. We can also just forget about street machines and just think about algebraic automaton theory. But I still think that it's kind of interesting. There might be some categorical language we can talk about this thing that can add a useful tool or useful perspective. And I think there's another thing which is, might be a crazy coincidence, but there is some tantalizing kind of hint of something, which is that so Rhodes actually has a book. I don't know if you know it, which is absolutely crazy. It's a book that was known, I think, as the Wild Book. It's like something he wrote and hasn't published, and like people has been passing it around as a manuscript, like something. And it's like a book which I don't remember the full title, but today it's finally published. But it's kind of, he talks about Krohn-Rhodes theory, and then he applies this theory to physics. Let's see, what was it? It was like, I think, physics, philosophy, psychology, and like, basically he says, oh, we're gonna now solve all fields of science with this theory.
Wow, I thought only physicists did that. I thought only physicists did that.
Yeah, not only physicists. Not only physicists. So it's pretty insane and kind of hilarious, but I think that it's not like 100% crazy, only 99% crazy. and like the 1% is that I think there's really something interesting in how you can like use compositional structure to think about like different things. I mean, he actually talks about the idea that we want to have like he actually talks about things that come pretty close to what I'm talking about here in the section of physics at least, not the psychology, but in the section of physics he talks about things like like in order to have like what does it mean to have a good theory that like explains the phenomenon. Like it's not enough to just have an equation because you cannot solve the equation. You also need like some kind of structure, and he like suggested kind of compositional structure of Krohn-Rhodes as kind of the type of structure that can allow you to like efficiently use a theory to reason this out. So that's not that far from what I'm talking here. And he doesn't talk about learning theory there, but the interesting thing is in that book, he introduces a complexity measure, which is pretty interesting. It talks about when you decompose an automaton into those prime components. So there's components that correspond to simple groups, and there's like the special component which doesn't correspond to a simple group. And so in this whole decomposition is it's non-commutative, like the order is important. And like the number of, he defines a complexity measure, which is the number of times you need to switch between group-like components and non-group-like components when you write this decomposition. And he kind of declares it to be like a very important complexity measure. Doesn't give a lot of justification, but it does analyze some mathematical properties of it. But the interesting point I'm coming to is that when you're talking about learning state representations using regular decision process, the thing we talked about before with the password problem, then if you look at Rhodes complexity 0, then it means that your machine is a permutation automaton. So like every action you feed, every symbol you feed into a machine acts as a permutation of the states. And it turns out that in this case, if you apply this constraint, then those kind of RDPs, that are kind of permutation RDPs, are easy to learn. You can learn them efficiently. You don't get the password problem there. And this leads to a crazy conjecture of mine that maybe like this Rhodes complexity is the correct parameter to talk about the difficulty of state representation. And it might be completely wrong, but there is at least some hint that it might be hard. So,
So in these machines or automata, it's like there's no notion usually of probabilistic transitions as well.
yeah, it's kind of deterministic. So so we would have to, so for this to make sense, for this to apply to like RDPs, we would need to come up with some decomposition theory for probabilistic automata. I think I googled it. I don't remember whether I found it or I haven't found it. but I don't know. It at least seems plausible that something like this can exist. Like I can imagine something that you need like an additional type of prime component, which would do, because like in some sense, like all the kind of permutation-ish irreversible transitions, they correspond to prime components, which are like simple groups, and then like the irreversible things, they correspond to the other type of component. So I imagine that maybe like probabilistic things, they also add like a new type of component, or maybe it's like component with some, there could be something like that. I mean, like probabilistic thing is in some sense the probabilistic thing is kind of continuously interpolates between irreversible and reversible. So maybe you can kind of decompose it into irreversible plus something that's just partly. I don't know, but it's interesting. It's possible. Yeah. So algebraic automata theory doesn't talk about probabilities. The same does talk to some way. Right, so there's those things, and then there's the compositional Polytope MDPs, which, as you know, is like this formal language for which we already kind of know, although you're talented to write it properly, but it seems that we already know that there is some efficient algorithm for finding the optimum poles, which doesn't mean we can efficiently learn it, but it's already some use. So this already can set at least some kind of a toy model of, to show that, you can have like compositional structures, natural compositional structures that can be used for algorithms.
Sorry, quick question. I guess I feel confused why you think it's possible we can't efficiently learn it. As in, like, it feels like most of the work here is just like switching from doing this linear programming problem to just like doing some version where we're sampling data, and like it seems like we should be able to, or like it seems like we've already can do that or something. I don't know.
I mean, I'm talking about learning it in the setting where you don't already have the compositional structure, but you can discover it.
Right. Yeah. That seems harder. Okay, that makes sense.
Where we discussed it, it's not even clear what the assumptions should be, because like there are different ways to just kind of state representation problems and so on.
For tree machines, like, I mean, since like this was I guess implicitly brought up in the like string machines on spaces too is too expressive thing. Are there any avenues you've thought of like what sort of bounds on like the complexity of that the inner function defined by like the functor that's a single transducer is supposed to be like, because that is presumably some function that needs to be like, that needs to have some sort of computability bound on it. I mean, it like just like is that something you have ideas on? Because I didn't like see a lot of specifics about that on the original post, except like some through what I can infer from the examples.
I didn't have a lot of ideas, but just because I haven't thought about it much.
Okay.
I mean, it seems like there's like some stuff in the way of like you need to kind of prevent the transducer from like you kind of need to limit what it's allowed to do with its variables.
Yeah. I guess like it makes, because I was thinking like, probably like each of the description complexity classes in terms of, string machines needs to, assume some sort of complexity bound on the inner function or like the inner functor of each string machine in turn. But anyway, it seems like some of the examples use like regular transducers as the built-in blocks. Is like each string machine can just be like a regular, like can just be like a finite state machine, can just be a finite state transducer, an okay starting point.
I mean, sort of. Okay. In string machines, there's like another aspect there because there I also care about tree automata because I also want to use those for metacognitive agents.
Okay.
It's kind of so for the metacognitive agents application, it's kind of more tricky because like what kind of transducers we want to use. Like for kind of word automata, you can say, okay, we're only allowed to use like even order chains.
Right.
Also, there's like in the list of potential problems for project B, there's some kind of conjecture that I've been worrying about. I think that this we'll probably talk in detail later, but there's like some conjecture that tries to link lattice theory with kind of graph theory and random walks. And this is something that's kind of trying to argue that it's like something like an argument in the direction of if we have some particular types of compositional structure on our hypothesis class, then we should be able to learn it efficiently using Markov chain Monte Carlo methods. And so kind of thinking about that, so I guess we'll talk about this more later, but it's still, there's still like, even if this conjecture is true, there's still like a lot of steps to link between that and how do you get like a hypothesis class which has like this type of compositional structure, but this is like another interesting kind of possible hint on this whole attempt to invent compositional learning theory.